Okay, let's go through a couple more problems and we'll pick up the pace a little bit. So number 2, to demonstrate that all objects fall at the same rate, Mr. Robbins drops an apple and a bowling ball off the roof of Roosevelt School. Student films this and determines that it took 1.5 seconds between the time when they were released from rest and when they hit the ground. While they were falling, each object was accelerating at a rate due to gravity, which I should say is an acceleration of 9.8 meters per second squared. Okay, so what do we know in this problem? Now, the thing that's not really important is what he dropped or how he dropped it or how many things he dropped. The bottom line is he dropped something and it fell from rest. So that tells us our initial velocity is 0 meters per second. Okay, there we go, released from rest. And it took 1.5 seconds between when he let it go and when it hit the ground, so we know the time interval. The other thing that we know is the rate at which the objects were accelerating as they fell, which is the rate due to gravity. So I know 3 things now. With these kinematic equations, once I know three of my unknown variables, I can solve for the other 2. What am I being asked for? 2 things. A, how high above the ground did Mr. Robbins drop the objects? Okay, so that would be equivalent to the displacement of the objects as they fell. And then how fast were the objects moving at the instant before they hit the ground? This is something that some people get confused about. They go, well, the final velocity must be 0 because they hit the ground and they stopped. Well, that's true. That happens because the ground pushes on the object. It exerts a force to make it stop. But what we're interested in is how fast is it going right before that happens? You can imagine almost an infinitesimally small distance above the ground. So let's draw a little picture. So there's my person at the top, and they're going to take this object and they're going to drop it from rest, and it's going to go ahead and smack the ground. And like right before it smacks the ground, it's got some velocity, final velocity, and it has an initial velocity of 0. There, my displacement is how far that is from where he let it go to the ground. And I could actually use this to approximate the height of the building. So let's go ahead and choose a mathematical model to use. I know initial velocity, acceleration, and time. The first thing I'm going to want to solve for, just take a peek, was the displacement. Okay, how far did the objects fall? So I look at my first equation. Can I use that? I can't. It doesn't even have displacement in it, so forget that one. I look at my second equation. It's got displacement in it, but it also has final velocity, and I don't know that. That's not one of my knowns, so I can't use that equation. How about this one? It's got displacement. That's what I'm looking for. Initial velocity, time. I know both of those. I know acceleration. Okay, good. So this third equation, that's a possibility. It seems like I could use that to solve for the displacement. Let me check the third one just in case. And I see, now here's a problem. It's got final velocity in it as well as my displacement, so there's 2 unknowns in that last equation. So I'd better stick with that. I'd better stick with that third equation. D is equal to V naught T plus 1/2 AT squared. Okay, let's go ahead and I don't have to do any algebraic rearranging here because I'm solving for D, and there it is all by itself to the left side of the equal sign. So I just have to put in what I know. We know that these are going to, the product of these is going to be 0. But I'll write it anyway just to show it all out. Okay, so like I said, that's going to go to 0. I basically put this into my calculator, half of 9.8 times 1.5 squared, and I get approximately 11 meters. And let's see, do my units work out? Let's see, here I have meters per second squared. There I've got seconds in the numerator, and I square it. So I'm left with meters. Yes, that works out because I want my displacement in meters. So it tells me that the objects fell about 11 meters. I'm rounding to 2 significant digits here because I can see that I don't have any more than 2 in my knowns. So let's take a look at B. In part B, it says how fast were the objects moving the instant before they hit the ground. So that would be this final velocity. So after 1.5 seconds of being accelerated by gravity, how fast are they moving? So let's see, which equation can I go ahead and use there? I know V naught, A, T. Do I want to use D? once again, that's a risk. And remember, also in this case, this is probably rounded because I've only had two significant digits. So you know what? I'm going to stick to my knowns. And I'll look at my first equation. Oh, there's final velocity. Do I know initial? I do. Do I know A, T? Yes. So I will go ahead and choose this mathematical model. And again, no algebraic manipulation needed here. Final velocity is equal to 0 meters per second plus 9.8 meters per second squared times 1.5 seconds. And when I go ahead and do that out, I put that into my calculator and I get a final velocity of 15 meters per second with my rounding to two significant digits. Okay, and just for those of you that are wondering, that's about 33 miles per hour. So, especially depending on what the object is, you don't want that falling on your head. That's pretty fast. If it's a heavy object like a bowling ball, I would definitely want to stay out of the way.